Management models, mathematical tools, optimization models. First, we will remember the basic concept of optimization involving one variable functions, and next we will see how to generalize to multivariable functions. A global optimum of a function f of x is a point that provides us with the best value for the objective function, that is the highest possible if we maximize, and then we call it the global maximum, or the lowest possible if we minimize, and then we call it global minimum. Then a local optimum of a function is a point that provides us with the best value for the objective function, but in the surroundings of the point. That is the highest possible if we maximize, and then we have a local maximum, and the lowest if we minimize, and then we have a local minimum. That is, for those points close enough to the local optimum, the value of the objective function will always be worse. However, if we move away from the local optimum, we may find another point with a better value for the objective function. Let's illustrate this global versus local optimum concept with a graph of a function. So, if we look at this function, and then we can identify here, this is a local maximum, that's a local maximum also, and that would be the global maximum. That's the highest value of the objective function, and these are a highest value but only in the surroundings of the point. But if we move further away from the point, then we might find points that have better value of the objective function. Now the same happens for the lowest value, or the lowest in the surrounding. Then we may have here the lowest one, that would be local minimum, that's the local minimum, and there would be this global minimum. Okay, that's for one variable function. Now, what are the conditions for finding out this locally maximum or minimum, or this global optimal points? Then there are two conditions called the first order condition and the second order condition. The first order condition is designed for finding out the so-called critical points. These critical points are these candidates for being maximum or minimum. And the condition for being a critical point is being a solution of the equation first order derivative equals 0. Because if we have a local optimum, then this must be compulsory a solution of such equation. So first step for finding the optimal, the maximum or the minimum points of a function is to state and solve the equation first order derivative equals 0. Okay. Once we've got the critical points, so the solutions of this equation, then we check the second order condition. The second order condition says that if we have a critical point and we substitute that critical point at the expression of the second order derivative, then if this is a positive, if this results in a positive number, then we have a local minimum. And if we get a negative number, then we have a local maximum. So the combination of the first order and the second order conditions allow us to find out those maximum or minimum points of the function. Now let's see what happens when we have a multivariable function. And we will see that these concepts are generalized in the standard way. First, if we start with a multivariable function, and in this course we will focus just on two variable functions for the purpose of optimizing, two variable or at most a three variable function. So the global optimum of such a two variable or three variable function is a point, and this point will have two or three coordinates or three coordinates such that provide us with the best objective function value, the highest if we maximize, the lowest if we minimize. That's the global optimum. And this local optimum is the same idea, the highest or the lowest in the surroundings of the point. But if we move too far from the point, then we might find better points. Okay, so same way, if we want to illustrate that, then we can draw a two variable function like this one, and it's going to be a surface, and this surface might have some local maximum there and a global maximum there, and then we might have let's forget about this initial, and that is also a local maximum. Okay, and the same with the minimum. Also, it's not so obvious, but with the maximum it's very easy to understand that it works the same way as with the one variable functions. Now, what happens with the second order conditions or the first order conditions? What are these conditions for finding out the optimal points in a two variable function or three variable function? Imagine if we have a two or three variable function like f of x. The first condition is finding the so-called critical points, and for finding out the critical points we have to write down an equation system. Because it's a multivariable function, then it's not like the first derivative equals 0, but the gradient equals 0. So we have an equation system like the partial derivative according to x equals 0 plus the partial derivative according to y equals 0. So we have an equation system, two variable, two equations. Or we can have three variable function, and then we will have a three equation system with the three partial derivatives of the function equal to 0. Okay, and that's the critical point equation system. To be solved in order to find out the critical points. Once we have the critical points, then we must use the second order condition. And now the second order condition is also slightly different, because we don't have just one single second order derivative, but we have several second order derivatives, as you know. We have a Hessian matrix. So if we have a critical point, it's going to be a point with two coordinates or with three coordinates, then we have to substitute such point at the Hessian matrix, and we have to find out the sign of the Hessian matrix. If the Hessian matrix is said to be positive, then we have a local minimum. And if the Hessian matrix is said to be negative, then we have a local maximum. And if it's said to be undefined, then we don't know. We have what is called a saddle point. So, but what does this positive negative Hessian matrix mean? We have the following definition. When is a Hessian matrix either positive or negative? So we can classify our critical points. Let's focus on a two-variable function because we're not going to study the second order condition for a three-variable function. We're only going to study this condition for a two-variable function. Let's write down the Hessian matrix when substitute at that critical point or at a given point. Then we have this second order according to x twice, second order according to x and y and x, which both coincide, and the second order according y twice. Then, if we assume that we have a Hessian matrix with determinant non-zero, then we can state the following definition. The Hessian matrix will be positive defined if the second order partial derivative according to x twice is greater than 0, and the determinant of the Hessian matrix is also greater than 0. So makes sense, that's positive and positive, so we say that the Hessian matrix is positive. And when we have the Hessian matrix negative, then the Hessian matrix is negative when the second order partial derivative according x twice is negative. That makes sense. But now something rather unexpected, that the determinant of the Hessian matrix must be positive. So negative, negative, it's not negative Hessian. A Hessian matrix negative is negative, positive. First negative and then the determinant also positive. Okay, any other combination, in any other case, we have an undefined Hessian matrix. Okay. So now let's see an example of how to use these first order and second order conditions for a two-variable function all in combination. Let's see the following example. So we have this function x cubed y cubed minus 3x minus 12y plus 20, and we want to find out the critical points, and then we want to classify such critical points using the second order condition. So we start by writing the critical point equation system, which is 3x squared minus 3, that's the partial derivative according to x, and the partial derivative according to y is 3y squared minus 12 equals 0. Now we have to solve this system, and it's easy if we just solve for x as the first equation, and we get x squared equals 1, so x equals positive negative 1. And out from the second equation, we get 3y squared equals 12, so y squared equals 4, and then y equals positive negative 2. And out of it, we have the following critical points, all combinations x and y. So we've got the 1, 2, minus 1, 2. Then we have this 1 minus 2. Sorry. 1 minus 2 and minus 1 minus 2. Okay, so now that we have the critical points, we come to evaluate the second order condition. And the second order condition we need the Hessian matrix. So we need the second order partial derivative according to x twice, that's 6x. Next, the second order partial derivative according x and y, which coincides with the other way around yx, and that's 0. And the second order partial derivative according to y twice, and that's 6y. So the Hessian matrix is 6x, 0, 0, 6y. And now I focus on each one of the critical points. I substitute the Hessian matrix at that particular point, and I get a numerical matrix. For the first critical point 1, 2, I get the matrix 6, 0, 0, 12. And then I check the conditions, either for being positive or negative. So in this particular case, I have the second order partial derivative according to x twice. At this critical point, it takes the value of 6, which is that value there. And the determinant of the Hessian matrix is equal to 72, which is both are positive. So the Hessian matrix is positive, and so we have a local minimum. And we continue to the next point. Next point is 1 minus 2. And now the Hessian matrix 1 minus 2 is 6, 0, 0, minus 12. And so we have second order partial derivative according to x twice is at 0.12 is equal to 6, that's positive, but the determinant of the Hessian matrix now is equal to minus 72, and it's negative, but this combination is undefined. So if it's undefined, we have a saddle point. Okay. Next point is minus 1, 2. Hessian matrix equals minus 6, 0, 0, 12. And so we have second order according to x twice, minus 1, 2 equals minus 6, that's negative, and the determinant is also negative. So negative, negative, it's not negative, it's undefined. So we have again a saddle point. And finally, we have a last point, last critical point, minus 1, minus 2. The Hessian matrix minus 1, minus 2 is equal to minus 6, 0, 0, minus 12. And now we have this second order x twice equals at, when substitute at this minus 1, minus 2 equals minus 6, negative, and now the determinant is positive. It equals positive 72. So this combination is for negative. So we have a local maximum. So our two optimal points are a minimum and a maximum, and this is the maximum and that is the minimum. So this second order condition is in fact a way of checking whether the function is locally concave for maximizing or locally convex for minimizing. So these are the concepts of concave or convex. Let's remember the definition of what a concave convex function is. Let's start with a one variable function. Then a function is said to be convex if the segment joining any 2 points on the graph of the function lies above the function. As if I have a segment like this, then the segment is above the function. If I have a segment like this, then the segment is above the function that lies below. Okay, that's the idea. So when this happens, the only possible shape for this to happen is that of a convex function, that type of shape. And if we have a two-variable function, then this two-variable function is convex, the same idea. If the segment joining any two particular points there is always over the function, the same idea. And this only happens if the function has that particular shape. For concave functions, it's the other way round. If the segment that joins any two particular points on the graph of the function is below the graph of the function, then we have a concave function. And for a multiple variable, it's the same type of shape. And now if we join two particular points on the graph, then they are below the graph of the function. So this should be like this because it's under. So we're not supposed to see it. They are below the function. Okay. So these convex and concave functions have a very strong property concerning optimal points, because if we have a convex function, because of its shape, then any critical point is automatically a global minimum, because the second order condition with the Hessian is the same as the condition for a function to have that particular shape of a convex function. And in a concave function, any critical point is automatically a global maximum, because that is the second order condition is the one that proves that the function has that particular shape. Optimization models in economy, maximizing consumers' utility under a budget constraint. In economic theory, one of the most emblematic optimization models is that of maximizing consumers' utility under a budget constraint. Therefore, we have to state and solve a so-called constraint optimization type of model. The general field of constraint optimization models is beyond the scope of this course. We will just focus on the optimization model used in consumer theory as representative of such type of problems. Let's start with the definition of a maximization problem with an equality constraint. Let's consider a two-variable function fxy. A maximization problem with an equality constraint is defined as the optimization problem aiming to find the point or points where the function takes its maximum value, provided that the constraint is satisfied. It is denoted as follows. We write the max, or if it were a minimizing problem, min, and then we write the function, and then we state such that, and we write the equality constraint that must be satisfied. So this definition just put together the two elements in a constraint optimization model, the one of the objective function, what is called objective function, and then that's the constraint. We will only study the situation where we have an objective function and one single equality constraint. Let's see the standardized example that we are going to approach. We are going to have an utility function like this one, 2x cubed minus 9x squared minus 6 plus 20. As usual, x and y denote the amounts of two goods A and B. The unitary price of A is this time 2 euros and the unitary price of B is 1 euro. Then the consumer has a budget of 6 euros that wants to spend in full. Let's write the formal expression of the utility maximization problem under the given budget constraint. So we have to maximize our utility function 2x cubed minus 9x squared minus 6y plus 40 such that the following budget constraint is satisfied. 2 times x plus y equals 6. Unitary price of A times the number of units of A, and then the unitary price of B, that's 1 times the number of units of B equals 6. And that's the constraint optimization problem that we want to solve. The first and second order conditions, optimality conditions of a constraint optimization problem are similar to those of an n-constraint optimization problem, but stated in terms of a particular function called the Lagrange function. Instead of using the original function, we have to build a new function that puts together the function and the constraint. Let's see the definition of this Lagrange function. Let's consider the following constraint optimization model. We have an objective function fxy. We have an equality constraint a1x plus a2y equals b. Then the Lagrange function of such optimization problem is the following function. We have this L for Lagrange, x, y, m lambda. And this lambda, this is a new variable. And the function is built as follows. First, we write the original function, next plus, and then we write this new variable lambda times the constraint written always like that. First, we write the right-hand side minus all the elements on the left-hand side and not the other way around. So it's that way. Then the Lagrange function has these original variables x and y and an additional variable called lambda, and that is called the Lagrange multiplier. So let's see an example of how we build this Lagrange function. We have the utility function. This is our model maximizing 2x cubed minus 9x squared minus 6y plus 40 such that that's 2x plus y equals 6. And we want to write the Lagrange function of this problem, and we have L of x, y, and lambda equals the original function. We just copy the original function, and now plus the new variable Lagrange multiplier times, and the budget constraint written this way: 6 minus 2x minus y. Okay? And so this is what we call the Lagrange function. And as you see, it's a function that puts together our original function, that's the function itself, and that's the constraint. And they're together connected by means of the Lagrange multiplier. So we continue, and now we're going to state the optimality conditions for a constraint optimization problem. So now we're going to focus on an optimization problem where we have our objective function, and then we have one single equality constraint. We have a Lagrange function associated, where we have this original function, the Lagrange multiplier, and then the constraint written as b minus a1x minus a2y. So what's the first order condition? The first order condition states that if I have a local minimum of this constraint optimization problem, that is a point that satisfies the constraint, so it's a point that both satisfies the constraint and optimize the function. So if I have such a local optimum, then the gradient of the Lagrange multiplier, that means the gradient, not the gradient of the function, but the gradient of the Lagrange multiplier, is equal to the 0 vector for a suitable value lambda of the Lagrange multiplier. Okay, so the first step, the first condition for finding out the optimal points of a constraint optimization problem, the so-called critical points, is to write a system involving the partial derivatives of the Lagrange function. So it's a system like the partial derivative according to x of the Lagrange function equals 0, the partial derivative according to y of the Lagrange function equals 0, and then the partial derivative according to the Lagrange multiplier also equals 0. And this is now the critical point equation system. In the second order condition, now we calculate the Hessian matrix of the original function f, and we substitute our critical point. And as with the unconstrained problems, if the Hessian matrix is positive, then we have a local minimum with Lagrange multiplier lambda 0. If the Hessian matrix is negative, then we have a local maximum with this Lagrange multiplier, and if it's undefined, then we have neither a minimum nor a maximum, and what we have is a saddle point. Let's see the following example, and let's try to solve this constraint optimization problem using the Lagrange function and its second order condition for classifying the critical points. We start by writing down the Lagrange function of this optimization problem, and we have maximizing utility minus 3x squared plus xy minus 4y squared such that 3x, unitary price of A is 3 and y is 1 and a budget of 6. So our Lagrange function is minus 3x squared plus xy minus 4y squared plus lambda times, and the constraint is 6 minus 3x minus y. So that's the Lagrange function, and now the partial derivative of the Lagrange function according to x is minus 6 plus y minus 3 lambda equals 0. The partial derivative according to y is x minus 8y minus lambda equals 0, and the partial derivative according to lambda is equal to 6 minus 3x minus y equals 0. So if I consider the second equation and I solve for lambda, and I get lambda equals x minus 8y, and I have this first expression for lambda. And now if I consider the first equation, and then I get 3 lambda equals minus 6x plus y, and so lambda equals minus 6 plus y divided by 3. That's our second expression for lambda. And if we put together these two expressions for the same variable lambda, then we get an equation only on x and y. If I do all the calculations here, then I get 9x equals 25y. So x equals 25y divided by 9. And I have that expression for x, and I move to the third equation. I do the substitution, and I get 6 minus 3 times 25y divided by 9 minus y equals 0. So I do all the calculations, and I get 6 minus 28y divided by 3 equals 0. So y equals 18 divided by 28. So I come to do the substitution there, and that if I simplify is 9 divided by 14. And if I do the substitutions there, then I get x equals 9 divided 14, 25 divided by 9, that means 25 divided by 14. So x is equal to 25 divided by 14, and with both x and y, I go to the equations of lambda, and I get a value for lambda, and lambda equals 25 divided 14 minus 8 times 9 divided 14. If I do all calculations, I get 47 divided by 14. So I have as a critical point, one single critical point, that is xy equal 25 over 14 and 9 over 14 with a lambda equal 47 divided by 14. And now I have to check the second order condition for this critical point. I focus on this second order condition. I have to calculate the Hessian matrix, and for that I need second order partial derivative of the function x twice, and that is minus 6. Okay. Then I need second order partial derivative x and y, a second order partial derivative y and x, and that's 1. And the second order partial derivative y twice, it's equal to minus 8. So the Hessian matrix is minus 6, 1, 1, minus 8. And if I consider it as if substituted as current critical point 25, 14, 9, 14, with this multiplier 47, 14, then it's same matrix, nothing to substitute for, and the second order partial derivative x twice is minus 6, which is negative, but the determinant of the Hessian matrix is 48 minus 1, 47, which is positive. So negative positive means that we have a Hessian matrix negative defined, so if it's negative defined, that means that the critical point, that is a local maximum. Let's focus on the economic interpretation of this constraint optimization problem. In economic theory, there's the following principle. When a consumer is maximizing utility, the ratio of marginal utility to price for all goods is equal. This economic principle from consumer theory is a direct consequence of the mathematical solving process of a constraint optimization problem. Let's state it, and let's prove the economic formula that's usually used. Consider the following constraint optimization problem of an utility function, and then we have budget constraint. Formally, this is like maximizing an utility, and then we have the price of the first good and then the price of the second good, the price of A, the selling price of A, the selling price of B. So that's our budget constraint. Now, if we write the Lagrange function, then it's like that. And if we write the equation system for finding out the critical points, then that would be the partial derivative of the Lagrange function it's going to be the partial derivative of the utility function according to x plus lambda is a constant multiplying that remains the same, and if I derivate that expression, there according to x, that's 0 minus px, then the derivative of x is 1 plus 0. So it's like that. That's the first equation. The partial derivative according to y is very similar. It's the partial derivative of utility according to y, so that's the partial derivative of that part of the expression, and then plus the multiplier times 0, 0, and minus py. That's minus. Okay. And that must be equal to 0. And finally, the partial derivative according to lambda is equal to 0 plus lambda turns into 1 that multiplies b minus px times x minus py times y, because that's a constant multiplying that remains the same, and this must be equal to 0. So if we follow the same process as before and we try to find out the critical points, then we solve for lambda at each one of the first two equations, and we get lambda equals the partial derivative of utility according to x divided by px. And from the second equation, because this is like partial derivative of utility according to x equals lambda px. So if I move this to the other side dividing, then what I get is that equation. And the same for the second equation. I get lambda equals the partial derivative of utility according to y divided by py. Because those two lambdas are the same lambda, then the partial derivative of utility according to x divided by px equals the partial derivative of utility according to y divided by py. And if we put the prices together and the marginals together, then we get what is called the ratio of marginal utilities to prices. Okay, so this ratio of marginal utility is that one. It's the same as the ratio of prices, and that's the economic principle that is used in consumer theory, in economic theory. And for us, it's just a shortcut for finding out the critical point without really writing down the Lagrangian function and building the system as traditional way. Let's see an example of using this economic formula as this shortcut for writing faster the equations. So we have this example for maximizing utility, and we have a budget of 600 euros and prices P and 10 respectively for A and B. So if we write the principle, the ratio of utility to prices, then we have a partial derivative of utility according to x is 40 times 0.25 x minus 0.75 times y 0.5, and then we have the partial according to y equals 40x raised to the power 0.25 times 0.5 times y raised to the power of minus 0.5. So the ratio of marginals is the following fraction. So I write both derivatives, and because they look very similar, then I will try to simplify as much as possible. Sorry. 25 0.5 times y raised to the power of 0.5, and so here I simplify 40 with 40, then I put together these two x, and then I get x minus 0.75 minus 0.25, that means x raised to the power of minus 1. And then if I put together these two y's, then I get y raised to the power of 0.5 minus 0.5. Sorry, this made a mistake when copy. This is a minus. And I have y raised to the power of 1. Now, I continue simplifying, and then I get 0.25 divided by 0.5, and then times x minus 1 times y raised to the power of 1. And so if and that's one part of the formula, and the other part of the formula is very easy, is px divided by py. That means 4 divided by 10. Remember that the prices were 4 euros for x and 10 euros for y. So it's 4 divided by 10. If I put together the two expressions, then I get my first equation depending only on x and y. That's equal to 4 divided by 10. So this means that y divided by x, that's this part terms can be written like that, equals 4 divided by 10 times 0.5 divided by 0.25. Okay, and this results in 5, 4. This is equal to 4 divided by 5, 4/5. So y is equal to 4/5 times x. And so from the formula, economic formula, I get a relation between the x and the y, so that this ratio prices, ratio marginals is satisfied. Then I take that relation and I substitute it at the budget constraint. My budget constraint is 4x plus 10y equals 600. So if I do the substitution, then I get 4x plus 10 times 4x fifths equals 600. So if I do this turns into 8x. So it's 12x equals 600, so x equals 15. And I have the first value, the first coordinate of my point, that is x 50. Then I substitute that, the relation between x and y, and I get that y equals 4/5 times 50, which is 40. So y equals 40. So it's like a faster way of getting a critical point without really calculating the Lagrange multiplier, the lambda, without using this lambda. So the critical point is x and y equals 50, 40. And I have to determine whether this critical point is a maximum or not. So I have to check the second order condition. The second order partial derivative according to x twice is 40 times 0.25 times minus 0.75 times x raised to the power of minus 1.75 times y raised to the power of 0.5. And then the second order partial derivative x and xy is 40 times 0.25 x raised to the power of minus 0.75 that remains as a constant multiplying, and then 0.5 times y raised to the power of minus 0.5. And the second order partial derivative according to y twice is 40 times x raised to the power of 0.25 times 0.5 times minus 0.5 times y raised to the power of minus 1.5. Now I have to do the substitutions of these three partial derivatives at the critical point 50 and 40, and for the second order I get minus 0.0504, and we start by noticing that it's a negative one, and that's the first condition in our second order optimality condition. And now the x and y partial derivative, when substitute, we get 50, 40, we get 0.042, and now y twice, we get minus 0.1051. If we build the Hessian matrix, at our critical point, then we have minus 0.0504, 0.042, 0.042, and minus 0.1051. And I have that first order that is a negative, and then the determinant is positive 0.00353. So it's negative define the Hessian matrix of the utility function that is negative. So if negative, the combination of consumption 20 units of A, 50 units of B, that's a maximum. That's the combination that maximizes utility.